Good afternoon, dear members of the Scientific Council, dear guests. Thank you very much for the opportunity to present this topic, applications of precise magnetic sensors. Shortly about the agenda, I will quickly introduce the sensors I have been working with, their state of the art, and the infrastructure and calibrations I have used to develop them. And then I will show several examples from several areas I have worked in recent years. So magnetism is a very broad topic. I will concentrate just on a very small part, measurement of magnetic field vector in a range approximately plus minus 100 microtesla, which covers the Earth's magnetic field, why I will describe later. Typical applications in this case are ferromagnetic object detection using magnetic radiometry typically for various purposes, navigation, I mean compassing using the Earth's magnetic field, or using artificial fields, for example, for underground drilling applications, geological prospection, gold hunting. Gold is often found within other like ferromagnetic ferrous rocks, so this may be a possibility. Biomedical applications, certain heart diseases can be diagnostics of certain heart diseases can be easily done with MCG, but not so easily with traditional methods. And of course, there are plenty of scientific applications like Earth's magnetosphere observation and more. I will mention some of them in the presentation. As I said, our magnetometers work typically in the range of hundreds of microtesla, and we want to get as best resolution as possible, which means several picotesla right now, which means that fluxgate magnetometer can reach something like 160 dBs of dynamic range, which is quite problematic for the electronics because current analog to digital converters can offer something like 145. So we have problems to do proper data acquisition, but there are some ways how to solve this. I will mention throughout the presentation some parameters, so I just want to quickly cover them here. I will be talking about noise. By that I mean power spectral density, typically in picotesla RMS per square root of hertz at 1 hertz. Because the noise of magnetic sensors typically have 1/f character, so usually it's mentioned at 1 hertz, but for some applications, for example, these geomagnetic observations, lower frequencies are more important, but all the numbers here in the presentation are at 1 hertz. Of course, there are other parameters, linearity, temperature stability, and so on, but I think the most important one here now is the noise. Magnetoresistors, the first type of sensor I have been working with, not so precise, but very useful, but today we don't have time for them, so I will skip directly to fluxgate sensors, which is the topic of my work. They are much more sensitive, and that's the reason why in the presentation about precise applications I will concentrate on them. So in a very short way, I would like to describe the functionality. They can measure the static and slowly varying magnetic fields. So when we want to use coil basically to measure static field, it does not work like that simply, so we have to do something more. We have to employ ferromagnetic core and use the strongly nonlinear behavior of the BH loop in order to make the Faraday law to operate, let's say. So how does it work? We have ferromagnetic core. In this case, it is this racetrack shape, and we have some excitation coil. So when we run a current through the excitation coil, when the amplitude is small, we are in this part of the loop, so the permeability of the core is high. It can be several hundred of thousands typically. And so when there is some external field, the flux lines of the field are concentrated into the core. While when we are in the saturation part of the core, the permeability is equal to 1 basically, and the core is virtually invisible to the external flux. So we can see that there is some change of the flux within the cross section of the coil, of the pickup coil. So that's how the sensor works basically. And on the pickup coil, we get second harmonic voltage, which is then directly proportional to the measured field. Why I'm talking about that? Because the magnetic core properties, they basically define the most important properties like the noise and the offset stability and so on. So one has to be very careful when you designing it, operating it, embedding it, and so on. So what is the current state of the art in the fluxgate sensors? I've been mentioning the application, and when you want some magnetometer commercially, you can, for example, look at these two companies, which are worldwide suppliers of low noise magnetometers, and you can find something like less than 5 picotesla noise for the very low noise version of a magnetometer, either analog or digital in this way, in this case. So you can remember this number as a current state of the art. Of course, there is another type of a fluxgate sensor, so-called orthogonal fluxgate, developed, for example, by Mattia Buta here at the faculty, which can reach sub-picotesla noise, but these sensors have some problems, for example, with offset stability under some conditions. So these parallel fluxgate sensors are still very useful for some applications, even though the noise is a little bit higher. So shortly to show you how the sensors actually look like. In this case, the core has this racetrack shape or ring core shape. So all these are single axis sensor. These are dual axis sensors, and they can be either operated, as you can see here, or you can embed them in something like this and use a vectorial compensation of the measured field. Typically, all the sensors are used as a zero detectors, so there is some compensation of the external field. You can see that the noise of these sensors is 4 picotesla for this one and something like 2.5 for the biggest. So it's less than I was mentioning before. What you can think about this number, for example, I was sampling 100 picotesla square wave magnetic signal using this C-type sensor, and you can see the result on the picture over there. The amplitude of the waveform, 100 picotesla, can be compared to 65 picotesla of a typical MCG signal amplitude. So using this sensor, you could actually see something like the hard magnetic signature. So just to give you some impression what's the sensitivity like. Goals of my work, they are basically quite simple: to develop as low noise as possible, as stable as possible sensor. The goal sounds simple, but the way how to reach is quite complex, using specific treatment of the ferromagnetic core based on research on finite element simulations, on publications available, and so on. using specific manufacturing procedures, improving them, working on the analog and digital signal conditioning of the signal from the fluxgate sensor, developing state-of-the-art data acquisition, because as I said, the current state-of-the-art analog to digital converters are not like sufficient for what is capable the fluxgate, and of course using a lot of equipment for calibration, for testing, which I usually develop or manufacture using bachelor and master degree thesis of my students. Here is a short example from the development. For example, in this case, it's a simulation of the annealing procedure. These parts are permanent magnets, and along it, above it, sits the flat magnetic core, which is exposed in furnace like that to increase temperature, and it allows us to adjust the profile of the magnetic domains of the material, for example, from this longitudinal direction of the domains to this like more radial one, which through some processes leads to decreased noise of the sensor. We can observe that thanks to Kerr-effect microscopy, which we luckily have in our lab. Or, for example, for measuring the noise, recently, together with my master degree student, I have been developing a digital lock-in amplifier based on FPGA. Really, it proved useful for the measurements of noise. Calibration is a very important part of the process of development, both for the deployment of the sensors before actually using them or sending them to customers, but also throughout the process, because it can give us a lot of information how the orthogonality or sensitivity or offset is changed with respect to temperature, for example. So we can use either scalar calibration, which uses some static and homogeneous magnetic field. For example, Earth's magnetic field when you are somewhere in the forest, as you can see here. Then you basically try to minimize this condition, which is the sum of squares of differences between the magnitude calculated from the vectorial measurement here and from the magnitude measured by a scalar magnetometer, which measures only the magnitude, but typically with higher precision than the fluxgates. Here at the faculty, we use triaxial coil systems, but this is quite tricky because you should calibrate them before using them. And here, typically at this building, there is a high gradient noise because all the trams and subways around here, so it's not so easy to use it. So I'm finally getting to the applications. The first one is basically the traditional application of magnetic gradiometry, which means using several sensors to measure a gradient thanks to the decay of the field with a cube of the distance from a dipolar source of magnetic field. In this case, we were cooperating with Mr. Kletečka from the Charles University to locate a fragment of Chebarkul meteorite which fell into this lake, and by having one magnetometer aboard this boat, one having like 6 meters below the surface of the in the depths of, I think, 5 or 6 meters, we were able to locate the dipole anomaly here, and later it was successfully removed from the water. You can see on this picture that actually the amplitude of the anomaly was so high that it was visible even on the total field without calculating or using the gradient between these two magnetometers. So one application, another one, we have a great cooperation, I would say, with the Czech Academy of Sciences, with the Geophysics Institute, which operates Geomagnetic Observatory in Budkov. So we are able to test our sensors there. For example, this is like a prototype of observatory magnetometer, which allows us to do some long-term testing of offset stability of the sensors. We have been using it in the Budkov, but also in another observatory, seismological observatory in Kasperské hory. Here is a picture from a tunnel, Christina, which is there, and at the very end we placed our magnetometer to compare it with the data from neighboring observatories, for example, from Fürstenfeldbruck in Germany and with Konrad Observatory in Austria. And you can see that the red one, which is the instrument I have shown you, is having the lowest noise, basically, and otherwise the curves match quite nicely. We were guessing what is the situation here and here. It might be the spatial traveling of the diurnal variation, because the observatories were located like in a line from east to west, but we would need more data to confirm that. Another hopefully interesting application, we cooperate with this Mr. Kletečka from Charles University and his PhD student Marian Takáč on using our magnetometers aboard their UAVs, multicopters, for geophysical exploration, typically around some craters, like to look for the bodies which made them, again, meteorites or other effects. And for this purpose, we created a complete system of magnetometer which has onboard data storage and GPS system. So using a base station and mobile station on a drone, we can nicely map the magnetic field, the geophysics of the area we select. For example, here is a picture of magnetic field from Russia, from the place of Tunguska event, but the device was used in many locations worldwide, a lot in Australia, in cooperation with some mining company. Again, for example, can look like that in operation. Okay, let's continue with another scientific application. This system for cancellation or zeroing of the Earth's magnetic field was created for the, again, Czech Academy of Sciences, for the Geological Institute, which operates a paleomagnetic laboratory in Průhonice. And they have something similar in operation, but they wanted an upgrade of the system in a new building. So we have designed, developed, manufactured, and now we are testing a complete system for this paleomagnetic measurements, demagnetization of the rocks, for the geological measurements, let's say. I don't have time to describe them really, because I'm not sure if I could do that even, because it's quite difficult to understand sometimes. But this system, it was quite tricky. You can see the size is quite big. In reality, when compared to when you see it in a computer, in a model, in a simulation, it's something, it looks easy, but in reality it was quite difficult to make it, including, of course, all the electronics for the compensation and calibration of the system, temperature controller, and other things. This is a picture from testing here at the faculty, where you can see that it really suppresses the external field down to basically the noise of the magnetometer, which was used to measure these waveforms. So typically the residual field should be less than 1 nanotesla in the center of the coils to make the measurements or the operation of the magnetization work really well. And one of the last things I want to show you is this Lunar Vicinity Complex Environmental Explorer, which was a project within the Czech Ambitious Mission Call. And we were supposed to develop a combo of AMR, magnetoresistive, and fluxgate magnetometer for measurements of weak magnetic fields near Moon. Typically few nanoteslas, maximum 10, 20 nanotesla in the area of the Moon simply. So we did, the project was in the state of project development. So, but even though we were able to provide several prototypes of the sensors and measure their parameters, which again were quite competitive with respect to the noise we were able to achieve in this case. Unfortunately, the project proved to be too ambitious and expensive, so it was not supported for a further stage of the process. So it finished like that right now. Here is an example of application of integrated fluxgate sensor. So only this small integrated circuit is a single-axis fluxgate sensor. I'm showing that even though it is not as precise as it should be to be really part of the presentation, but it's actually the only commercially available fluxgate sensor. So I just wanted to show it because still many groups worldwide try to develop this thing, and they are not as successful as Texas Instruments. Okay, and last application of magnetic sensors for security. In this case, it's a Ministry of Interior project. It says detection of carried explosive devices, but of course with magnetometers we cannot detect the explosives, but only some possible fragments which can be together, like to make them more dangerous or lethal. So again, it's a gradiometer basically. Even though we prepared quite a complex, again, data acquisition electronics, in this case, the most problematic part was the signal processing for the data. In order to get something useful, we were testing simple gradient measurements of the full gradient tensor, but finally we finished with an approach suggested by my colleague, Mr. Janošek, that we used correlation of the gradient measurements to get rid of most disturbances which can be found in these urban areas. Okay, I just wanted to say that I'm trying to involve bachelor and master degree students in this development. All of these are master theses of my students. Each of them has something to do with either fluxgates or application of magnetometers. So just to present this, and as I do most of my teaching in cybernetics and robotics study branch, I wanted to show you that each of the robots my student created has its own magnetometer. Again, just to show them that it's not so difficult and it's sometimes very useful. So to conclude my presentation, I've been able to develop and use parallel fluxgates with state-of-the-art or even overperforming the state-of-the-art noise, and excellent linearity stability, and use it in many industrial and scientific application and cooperations. For the future, I would like to cooperate more on the geophysics applications because they are really interesting, and it could also bring some more commercialization of these sensors. And yeah, the critical mission is to attract more students because typically my students seems to be scared somehow by the magnetism right now. So thank you for the attention.
Thank you for an interesting lecture on application of magnetic sensors and the way how you attract the students for the science and teaching in this topic. Now the floor is open for the discussion.
Okay.
Professor Svoboda.
Okay, thank you. So I've seen and heard quite a comprehensive list of scientific applications. But I am curious, since I know very little about the topic. So what is the main challenge in designing fluxgate sensors? And what are the methods you are using for tackling the challenges? And related to that, what's your personal focus in designing the sensors?
Okay, so the most difficult part probably for me, for example, is the work with the ferromagnetic material, because as I said, it's the key for a really good sensor, because to do it really properly, you should be like a solid-state physicist and metallurgist and to know all the diagnostics methods which are used in this field, which is not definitely my case. So I'm fighting with this, but of course you can solve that by cooperation, for example, with, again, Academy of Sciences or some institutes in the Czech Republic, but it then takes time, and it's better to have most of the really important things in-house, but it's not easy. Basically, that's one part, but it also, as I said, the part of the electronics, of the signal conditioning is also very important, and it's what I do, what I like to do, to work on the signal conditioning. Recently, the digital way proved to be very interesting, as usually in many other fields. Even for the really state-of-the-art versions of the magnetometer. So that's it. And how do I work on that? Yeah, for example, on the ferromagnetic materials, as I said, we used finite element method simulations. There are ways how to simulate the structure of the ferromagnetic material, but it's very difficult. I have not been doing that yet. Because, for example, how you can see what's really inside, using the Kerr microscopy I have been showing, you can just see the surface of the sample. You cannot see into the bulk material inside. So it's really a little bit of black magic sometimes to do the processing of the material in a right way. But yeah, this is the most difficult part for me.
Okay, thank you.
Professor Hazdra.
Could you please...
a microphone, please.
Thank you very much for the nice lecture. And, well, I have one comment. Could you please critically, evaluate how you can improve your performance in presentation to make your lecture more understandable for students?
Well, for sure I could use less slides and talk slowly, not to trying to tell so much information as I was trying today maybe. But I wanted to show you something in these 20 minutes, and it's really difficult to to do it properly, probably. So, and yes, my English is not perfect. I'm trying to work on that. But
yes, if you want to be a lecturer, you have to consider it, yeah, and think about it. Thank you.
Thank you. Professor Havran.
Thank you much for your lecture. I am not from the field, but I would like to ask you about the stability in the long term in case, for example, that ferromagnetic material for your coil is aging. Is it making some big, let's say, impact on measurement stability, or is it not so important?
Basically, we have records of the data for weeks, months, for example, for some from the application as the observatory magnetometers, for example. The device I have been showing was used continuously several months, for example, at the observatory in Butkov, and we haven't seen anything like that. These devices are operated for years, and it's quite difficult to see really small change throughout the years because the offset of the magnetometer is something which is quite tricky to you can measure it by putting it into the magnetic shielding. Of course, you can rotate the sensor to get the value properly, but really to monitor it in a continuous way for a long time, it's not so easy because the field itself will change typically. So I don't think so that the aging that you would see some really significant effect from this. Yeah. It's not something that it would wear out somehow the magnetic core, I would say. So.
No, but in case it's used in aerospace somewhere for many years, so then it might be an issue. Yeah.
Well, in aerospace, it can be because it's exposed to multiple changes. For example, in the temperature cycling, yes. That might be for sure an issue in this case. But for example, the radiation is supposed to have negligible effect on that, or even in some cases, I have seen publications that it improves actually the properties in terms of noise. We have fluxgate magnetometers flying on many satellites. Some of them are in deep space on Voyager missions, and I think the noise observed by them is decreasing, both because the noise of the field in the interplanetary space is very low, but also because I have read some papers that it's because it was exposed to the radiation and it somehow decreased the noise, but I'm not sure whether is it really scientifically proved or it was just an idea of.
Okay, and if you mention that, what is the required temperature stability for your applications, because in case you really have such low variations and low values?
So it depends. For example, when I consider this application on the UAV, it can be quite critical because you can see that the drone is flying there and back. And in each case, the position of the sensor with respect to the Earth's magnetic field is different. So the calibration of the orthogonality, for example, of the sensor axis has to be very precise, should be calibrated with respect to temperature change, because when you do wrong calibration, you will get different number of the field going there and different from the other direction. But for example, in this software they are using for data processing, I think it's quite clever and they can get rid of this effect quite easily. So for this case, it's not a big issue, I would say, really big, because the temperature stability in this values of 50 picotesla per Kelvin translates to something like several nanotesla per, I don't know, 10 degrees of change. So this is quite negligible in terms of the anomalies they are usually seen in the field. So they are typically higher pronounced, but for example, for the observatory magnetometers, it's quite critical to have the offset stability very good, even though in these applications the temperature is quite stable usually because it's placed somewhere with stable temperature, but still it should be this very low number you could see in order to be qualified for the data to be placed, for example, in the intermagnet network, which is collecting data from all around the world, for the scientific purposes.
Okay, thank you.
Professor Svoboda.
Okay. So, can you assess how many % of the success is the smart design and how many % is the actual construction, the thoroughness of the construction? So if you can compare.
You are talking now about the sensor, the magnetometer, or the device, for example, on the drone, or
yeah. So someone comes to you with a problem, right? And you design the sensor, and then you have to construct it. And I'm just hesitating how many % of the end success is the, say, cleverness of the design versus the thoroughness of the construction. Because I suppose, naively, that bad construction, the actual construction, can definitely spoil success, can definitely, remedy the, or suppress down the clever design. I don't know, just asking.
I would say it's a difficult question. When you, if you have a good design and you do some error during the processing, of course the result will be bad. But I think, for example, the main principle I have been using in the sensors I have shown you is the change of the magnetization of the core from like the longitudinal one to radial one. This principle I have first used like in 2015 or 16. Since that I am a little bit improving it, and still sometimes it happens that the result is not as expected, and I'm not 100% sure what was wrong. So
okay, we can probably take it offline. And the final question, if I may. So at the end, what's the main challenge? It is the accuracy or the precision?
For some applications, we are more interested just like in the variations of the field, not the absolute precision. Even in the case of, for example, of the observatory measurements, sometimes the absolute accuracy is difficult to somehow assess, because the placement of the device, for example, in the tunnel, without really giving it some effort, like directing or aligning it using some laser references, it's not so, it's very difficult. But for some applications, I think almost all the applications I have been showing are more related to like the resolution rather than absolute accuracy. But we use the scalar magnetometers to reach the absolute accuracy, because in the case of these scalar magnetometers, their input signal typically, for example, the frequency is directly related to the magnetic field by some constant which is defined very well. So the absolute accuracy is then very nice. And when we do the calibration, then within some time also the input of the fluxgate sensor is quite accurate. So
okay, thank you.
Are there any other questions? If not, I would like to thank you, the presenter, the audience, for asking a question, and we will meet. Applause. And we will meet in 5 minutes in the ground floor in the room number 80, and I would like to ask the members of the committee, eventual reviewers, to join us.